of algebraic tree, we have something about how we create the topology. For example, you remember when in the unrooted tree here before, this is, let's go here. So now if we have a rooted tree, I mean, how we already create the unrooted tree in the topology, like because normally we start by having the taxa A, B, C, D, and want now to see if this is really the correct topology or not. The topology now, the shape of the tree. If this is for the unrooted, we are not talking for rooted tree for now, for the unrooted tree. If this is really the shape, the correct one, based about how they are similar to each other, what's the distance to each other or not. So how we solve this problem? This problem by solving is not easy to look for this. There is more than one proposal. We can use heuristic approach, or we can use Quartet Tree, which is the puzzling. This is now we will talk today about this. This is the simple way and easy way to solve such problem in the topology. So because we want to find our aim now, we want to find if we have given like A and B and C as a taxa, we want to construct such topology, but it should be the correct one, not the wrong one. This is the aim of here, which we call that. So now, and when we say by the correct one, we have to express what is the neighborhood relationship between those taxas. Not like randomly, it should make sense that maybe the distance taken into account or the similarity taken into account or how they are closer to each other. And as I said, this is not easy problem. We can look for other, we use heuristic. But now, because the example is just one, 4 taxa here, you can see it is just 4 element or 4 segment. But imagine if you have like, it's a 100 sequence. It's also difficult to use easy. And we said it's two ways. The best so far, we use the Quartet Trees. Now, the Quartet Trees puzzle, it's really a concept. We can take what we do in the Quartet Tree puzzle actually. It's always take 4 taxa. It does not take in more than one. I mean, this is the key idea of this algorithm. It just is a quartet, that means in which there are 3 only with the 4 taxa. That means it will generate all possible trees. Let's assume here we have the taxa, our taxa is A, as in the figure here, is B, C, D, E. This is our input taxa. And then I want to generate the topology. So the key idea of this algorithm is use Quartet Tree, and the Quartet Trees, which are just generate all possible trees, which has just 4 taxa. That means it should has only 4 taxa, not more than 4. That means from this all possible tree, then I will have such one. For example, it can be this one, or it can be this one, and it can be this one, and that means this is the all combination of these trees, right? And this is here the idea. Just this type of algorithm try to compute the all combination, and then it will by that, but it should be also a unique decomposition. Not like you can take all combination. No, it should be unique also decompositing in this, and that's why this algorithm at the end, when I do it like this, it will tell me what is the best or what is the good topology for those things. First, I will tell me for each 4, and then I will ask what's about the 5 element. Then it will tell me how we add the 5th element. That first. Now, in our case, we have just 5 taxa, but this result will give me the best 4 topology for the 4 taxa, and the remaining one, the 5th one, we can add it easily later. We can see how we use it. Okay, so.
Doctor.
Yes, sir.
Can you make the screen a bigger?
Oh, sorry. Yes, sorry. Is this fine now?
Yes, thank you.
Okay. Yeah, sorry, Professor. Professor, you are right. Yes. Okay. Yeah. Okay. So now here, this is how the way is going. Like given a 4 taxa, as we said. For now, how many Quartet Tree will generate it of this, and then always we use. That means instead, because the algorithm says it should be n if the board is 4, and now is n is 5, then it will be here 5, then we'll have maximum 5 possible taxa. For that means this is we call it substring, and this is important. For example, in the exercise or in the homework or in the exam, maybe I will give you n equal to 8, and then I will ask you to generate all the possible taxa, and then we say n of the 8. It will be also just taken into account how we generate more taxa here, and then you will see always I will have 8 position. It will be here 8, and each time I'll take 4 taxa, and at the end we'll have a different combination. And this it will look here. First, we start by the initial one, which is all taxa, and then say A, B, C, and then we ignore A, for example, here. As we said, just we start by A, B, C. Once we have A, B, C, and then we create the first taxa, and then we keep going. Then we said, okay, the second combination I will have A, C, D, E, which you can see it here. And that means here we ignore the B. The B is out. Right, and then I will go to the third one. I will have, okay, A, C, D, E, and then that means the A is out. That means you have to be unique, and then later, and then all those combinations. So at the end, I will have the all combination. Those combination actually is very important to understand it. And those combination I can also tell by looking for this alternative quarter tree encoding. This encoding is important for us. For example, this encoding I can set here, the first taxa is the n of A. That means A and B is close against or not C and D. So that means those are the close up and those are the close pair, because every time you will take just when we say 4 subtrees, that means 2 pairs. This is one pair, they are very close, and this is the other pairs. Right, and then given this here, this will give you all the collection. Then what about this one? This one is N is A, comma E against, this is the first pair, against the second pair, it will be B and D. That means this is here. That means the closer taxa is here. We are looking for the pair of A and B, and not I'm far away from C and D. Let's say it in this way. The closer A and B, and this is the far away, which we call it here, all possible, we call it here, this is the far away. And by doing this combination, you guess it will find all possible taxa, which has 4 subsequence or 4 all type of topology for the 5 taxa. And then from then we select the best one. So that means notes here we have to first, our interest to find what is the finding the quarter trees for each of the 4 taxa, right? And this we can do it selected as a random, regardless for the all possible of topology. And for example, here we have at the moment we have just contain all leaves, right? But normally in the end here we have in the beginning 5, and then you can see every time I remove 1 from here, and then we keep it here. And then we remove, for example, in the beginning we remove A, and we keep A, B, C, and D, and then in the second topology or second combination we remove B and we keep A, we remove B, and then we keep A, C, and then we see what is the taxa and C. But this is also unrouted because we don't know the route so far. And this here represent, this one is represent what is here. This is the first one, for example, here, which we call it, what is the number of nodes, which is the close to each other, and this is here, and this is going to this one, and here we have A, E against, this is here the one, and then we have the third one, B, E, where is here the B, E here, we have B, E here, and then we have the fourth one is here A and E, A and B, sorry, A and B, and this is we go here. So this is all the combination. So now what is the theorem here? What is our observation about this? Let's go to just here. Yes. What is our observation here? Here the idea of the quarter tree puzzle, actually it always, each time we take just, for example, 4, and we try to determine the optimal here. But how we determine this algorithm, which we are not going to cover it in this lecture or in this course, which we call fringe time distance. This will tell you how distance is A and B. That means why you put in this order, or see here, why in this order we put here, we said here, and this is because the closer is A and B based on what? Based on some distance. We'll see it later in the example, but here, and this is the computing of this distance. We use Einstein distance matrix, but we are not going to see what is the theory behind it. It's not like interesting for us, but just here. And this is the second one. The second step of the puzzle of the quartet tree puzzle is combine the tree which in the final topology. That means after that I want to combine them together to see what is the good one. But sometimes not easy to do it with the Einstein distance, and it will take to give us the wrong topology. Then they suggest instead of doing this, then go with the heuristic combination of the indeed. So when we say heuristic, now we know that heuristic not always give us the optimal one, but it gives us something is some very close or very similar, and that's why we can do it other by using Einstein distance for the using this as optimization, and this is we'll try to optimize as much as can. But sometimes it's not easy to do it. Then we have to go to make it fast or give us wrong topology. Then we have to go with the heuristic combination. So now the idea of heuristic combination, which is the step 2, we ignore step 1. Now we say step 1 is not possible for H3. We are not possible. Then we go with the step 2, because step 1 is just give you the 3 possible for H4 taxa. You remember this one here in the beginning? If we have, where is it? I think on the other slide, let's see. So this is here. This one, for example, I have A and C, then we have just 3 possible. We don't have more than 3 possible for A and C for the taxa. Everything is 4, but doesn't matter. So this one now we focus about the step number 2. Step number 2, let's go just take it into at the end, because and then we can see it clearly. Yes. So step number 2, it told you how to do it in the way of the heuristic, and it is minimize the error, which is we want to minimize the error. So what we start actually this is the steps. What we start by looking for the reconstruction, the tree topology. So now we have the taxa from A, 41 to the TK, right? And this is our all the taxa. And then I want to reduce the error or minimize the error. So how we do it by minimizing? This is the procedure. We have to follow this procedure. So in the procedure here, it tells you first how to minimize the error. Well, in principle, we can talk to reconstruct the tree by apply to the K at the short more than less than the quarter. So what we mean here, for example, if I have, let's say, here and here, let's say I have A and I have here, I will have B, right? And then I have, this is just one possible, C and D. Right, so if I have this taxa now, here, so how I will do it? Then we want to add a new one, which is not violation, the count, or not violation, the path. So here I have to take it into account. That means what is the smaller optimal? I have to take it, what is the neighborhood joins? That should be the one I want to add it. If it's close to A, I should add it here. But if it's not close to A, or if it's close to A, it's possible to add it here, or add it in this direction, or add it in this direction. But if it's not close to A, if it's close to A, I cannot add it here. I cannot add it in this way. For example, here it's not possible. This is the wrong one. If I add it here, it's wrong one, because it's not. If we look for the neighborhood join shapes or the neighborhood shapes, how they are close, this is not possible to have it in this direction. So that means I have to be clear where I want to use it. Let's assume this is the first one to optimize the one. The second one now, he said, the second step, this is the consideration. Try to add it in the correct place. So how I will do it in the correct place? So here it will tell me this is here. Let's assume we have said, he said, for each respective neighbor join for tk plus 1 to the t, we have t, and which is against or not closer to, or not closer, let's say not closer to t prime and t double prime to identify in the t connection. So where that means the key tk plus 1 can be not be added to according to this formula. So here let's assume I have t prime, here t prime, and here t double prime, and here I have t. So now if I want to add 1 here, then I have to, it should be not here because this is far away from the, which is will violate the counting. This is the path is far away. We don't want to connect it because this is not the good one. And here, if I will add it here, is not the good one. I should add it in this location, which is close to the T, or in this location, if this is, let's say, it's maybe it's also B, or in this location. So this is the correct way to add the new one, which we call it TK plus 1. So for the taxa when we do it. And by look for the lower accounting violation. And this here, and I repeat this one and repeat this one until I have to construct the tree. Let's just to understand this here, we have to take this example, and then we can see how we add this. Let's take this example. Now we have the input is A and B and C and D, for example, as a taxa, and now I want to add this one, and we have, this is the initial one. It's already in, this is, let's say this is the good one or the optimal taxa for taxa, and look like this. Now I want to add E, right? When I want to add E, I want to see where I should add it. What's the best way I want to add E? So if we said I want it closer to A, if it's E is closer to A, we by doing the similarity or the distance, then I will say it will be here A, comma A, and not closer to C and D. So this one or this annotation tell us now, it tell me A is closer to A and not closer to C and D. So if it's not closer to C and D, I have, when I build it, I have to build the tree, I have to give some penalty here. I give some value, and this is to make those branch far away from E. And then I will say, okay, this can be happen fine. I can say this is here, this is the original one, this is here A, and this is here the B, and this is I have here C and D. So now to make this condition valid, not violation, then I'll say this should be 0, that because are closer to that. This is not taken into account, then it's because I say that I'm not saying he's not closer to B, then it should be also 0. But I'm saying this is also 0. But what I'm saying here, I'm saying this is not closer or not closer to C and D. That means I will change the branch. That means give them penalty or add a cost to this. If you want to put it here, it will be 1. And if you want to put it here, it will be 1. That means those now, the cost, this is 0. That means it's possible to add it here. It's possible to add E here. It's possible to add E here. But it's not possible to add E here or here. Why? Because now the branches of the topology of the tree, it's increasing by 1 here. That means this is costly more than this one. This is the first step. So I want to take the whole combination. This is the first one. The second one and this one, it can be, I can say this one also can go to, now I said N, the other possible, because I want to look for the other possible, right? I can say N, for example, here of, now I'll say B and E closer. Sorry, this is E. I'm sorry, this is just the writing. And E closer and not closer to the, let's say, I will say here C and D. So how the tree it will look like now? It will look the same tree. And the same one. And I will update the branch costly here. This is here C, and this is D, and here is A, and B. So this one tells me that I can, should be this still this 0. It will be still this is 0, right? It's still this will be 0. That means if it's 0, that means this is the possible for adding E, other E, I can add E here, or I can add it here, or I can add it here because the cost is 0. This is the minimum cost. But if I want to add it here, now when I say this is, I'm not close to the C and D, then I will add another cost. 1 here, it will be here, update to the 2 and is 2. So now this means if I will add E here, it will cost me more because this is far away from the remaining. That means this is wrong. If I will add E here, it will be wrong because now when I update the bridge, the edge, it will be 2 here, and it will be more costly. This is not wrong. So now this is the 3 possible way to add it here because they still have 0 distance or close very hard. This is far away. So based on what? In the condition when I put it to generate the tree. And then I said, okay, from this one, I can go also another step. And I said N, right? I said it's A and E also again. Always we put E because E, the one I want to add it, and not closer to the A, to the B and C. So now I include B in the combination. So that means our tree, it will look here. And I will update the cost. So here. So here I have A, I have B, right? And then I will have here C and D. So now the cost here, it will be different. So here is 0, but when I say here not A and E, this is E, yeah? When I say here not B, that means this branch, it will be now 1, because this branch also connect to the A, and this edge, it will be also 1. This will be 0. C and D, it will be remaining. This C, it will be now 3, because C is not, we say not C. C, it will be 3, and this will be 2. So now the cost here, and the possible way to add E, only this location. I cannot add it other way, because here it will be expensive, here expensive, here expensive, here expensive. Right? And then I said, okay, what else? Then I can add another combination. The other combination is N, like for example, it will be here, A, comma A, and then not, let's say we have what's here, yes, here we can say, we can B and D. And then this will give us the tree, it will look the same one. Here, but I have to update just the branches. So now it's not to the B and D, and here B is 1. When we say not, that means we will increase it to 2. Here the B, this will be 0. This one, it's 1, but when we say not B and not D, this is the path it can go here. Then I will say here it will be 2, and this is the remaining 3, because C, we are not touching C. It will be here the C will be 3 again. Here we are saying not D. D is 2. I will update it because I say not D. That means make the penalty of D is high, then it will be 3 here. So, right? And then let's say here to see it, the same thing. We are demonstrating here. You can see here at the end, by taking all possible, then at the end I will add it. This is here. And I say this is here. For this tree, for example, now we said this is here, this tree or this order is the next final tree for this topology. That means for the next step, this is the top. By adding a new distance E, this is the top topology. And you can see how the combination. The trick here always, when you say not, that means you have to add penalty to what? To the branch or to the edge. When you say not, you have to add the penalty. And you said here, and then you can do the old combination. So that's the trick here for the quantum tree. And by doing this, I think this is here. It's say, okay, if I have the initial one and I want to add only one element, the right length is here, or the correct length is here. And this is, we are finishing this the way. So it has some, for example, the extended can be randomization. Yes, we are selecting always the edge as the random, for example. Now because we focus to A, because or the closer, and also it's build the majority of the tree. Just this is here by we finish this lecture for today. Just quick things regarding if you have question you can ask, but quick things regarding the talk. So I think I didn't know, one of you said here we have public holiday or we have a break, and you already have a plan with your family, you will go somewhere, and you cannot attend it, maybe those talk, right? That's fine. I mean, I will send just a doodle. I will see how many of people they cannot attend this. You can check your plan with your family because this is a public holiday. If you have children, you want to spend time with them, it's fair. So we can move this one to here, or we can find another day to take it here, talk those. Or if we see the majority of the people they will attend and the remaining they cannot attend, we can also recording this talk. We will record them, and then the people they can listen to them later. That's fine. If it's okay now, are you agree with this solution? We have two solutions. Either we move it, or we can record it.
Yes, okay.
Okay, so fine. So try to fill the one is, I think some group is still missing. Try to fill this. This one thing. The other thing, the last thing. So I will be away from here until here. That means we will meet in the 15th. Our lecture will be in the 15th, right? So now we have almost like 1 week or 10 days. It's just missing. But I will encourage you also to work in the project. Yeah, I will encourage you to work in the team project. I mean, because I need you to just not like, of course, there is no lecture, but I will encourage you to work in the project because I want to see at least some improvement or tell me what they have done, what's the progress, at least when this, I mean, in the 13 or 15, I will ask you by email, what is the progress? I want to see some progress. At least now we have time. Just try to work in this one. Okay, guys, inshallah.
Okay.
Okay, so and also last thing for those that will want to do the presentation, I will encourage you to just send you the version, or we can meet like 5 minutes after you finish your presentation, before you present it, even like 1 day before you present it, just we can sit with you. I can sit with you just 5 minutes to see your presentation, if it's fine, if it's clear, and maybe I will give you some tips, and then just for 5 minutes before you present it next day, it will be good. Just we can do it online by team. Just contact me and I will look for your slides together, and I will tell you if it's really fine, or I will see the flow of the story, and I will give you some hint or some tips if something missing. Otherwise, it will be fine. Okay. So I'm really appreciate that you are stick with me in this lecture. You are not like complaining, and I know